All right, super. So thank you all for coming. As mentioned, this is the first time I've taught in a while, so I'm a little rusty. You might be also slightly less rusty as you had classes yesterday, but we'll get into the swing of things quickly enough. So let's see if everything works. So welcome to HQM1. So if you don't meet, I'm Associate Professor Will Horowitz. You can call me Dr. Horowitz, Professor Horowitz, or Will. I think that's about it. Whatever you feel comfortable with. Best way to reach me is wa.horowitz@gmail.com. Yes, I have a UCT email address, but Gmail is more reliable, I would say. Feel free to email me anytime. I'm generally very good with email and admin. If you don't hear from me in 24 hours, it probably means it just fell off my plate. Just email me again. I'm not going to be offended. Ben and Rachel can attest. Yeah, super. All right, so logistics. This should be, by the way, everybody can see this just fine. Great. All right, so lectures generally 9 a.m. to 11 a.m. Tuesday and Friday. Welcome.
Yeah, well,
please grab a seat. We've started. And great. Thank you for making it in. These are exceptional times. Morning. Okay, so normally 9 to 11, Tuesdays and Fridays. Thank you very much for accommodating me and the 8 a.m. today. This should be the last time it's 8 a.m. and then we're back to a more reasonable hour. Okay, tutorials. Maybe Tian can update us. My understanding is it's officially 2 p.m. to 5 p.m. on Thursdays. I understand that there are conflicts and there are movements to try to get that shifted to 11 a.m. to 2 p.m. on Thursdays. I'm agnostic. I'm just waiting on official word from the committee to take place. Okay.
Yeah, Andre has not responded yet. I will email him after the lecture to remind him.
Very good. Thank you very much, Tian. Okay. So as mentioned, we're beating all the lectures out on Zoom, so you can join virtually if you'd like. Welcome to join in person. I think it's better for me in person, whatever works best for you. Certainly, I know when there was COVID, it was very nice to just be able to roll out of bed and join a class, even to lecture a class. So I'm certainly very amenable to the virtual style. We will record the videos and throw them up onto YouTube. Hopefully I've received releases from all of you. Anybody have not received a release from? I have not received it. Please just quickly sign. It's really pro forma. Great. Very good. In principle, the idea is to send out homeworks on Mondays and have the homework due on Monday. I realized in the middle of the night that I had written the homework, but forgot to send it out last night. I apologize. That said, let me just briefly recap or check. Is the Monday due date homework good for everybody?
Yeah.
Okay, super, very good. Okay, and for the homework, send to ben.burt 1303. I'm giving you okay. Well, Gmail actually doesn't care about the dots, but let's,
all right.
Yeah. At gmail.com. Yeah, so actually, I introduced myself. Ben, please introduce yourself.
Ben, I'm the chief course. I'm doing a master's and working under Will. So I'm often in contact with him, but if you have any conceptual issues or questions, I'm helpful. I think the best way for you to deal with the conceptual issues is first talk to your friends, then myself, if you still have issues thinking.
That's exactly the right order to do things. Very good. Okay. So just in terms of the logistics, out on Mondays, on Mondays, I nominally put down 5 p.m. We need to make a time. I would say either 8 a.m. or 5 p.m. I feel like 5 p.m. is a good time. 5 p.m. is good. Very good. Now, your students, I was a student at some point, deadlines, ooh, they want to slip. We're not going to let deadlines slip. There are extenuating circumstances. We can go with that as it may. But the point is that if there are extensions, then things just pile on. So it's best just to turn it in. So as a sort of just a logistical hurdle or carrot or stick, however you want to think about it in terms of getting it in 5 p.m. on Monday, we'll take 10% off for any part of the day that don't recite. Do Mondays 5 p.m. and 10% off any part of day. So Tuesday is 10% off, Wednesday is 20% off, so on and so forth. It's fine. You do what you get done, turn it in, go to the next thing, revise when we get back. Good. Okay. So the exam, I proposed that the exam run in the middle of the VAC, Wednesday, April 2nd, 9 a.m. to 12 p.m. I feel awesome. Thank you very much. I feel like it's good just to get it over with. And then you have one less thing to worry about during the exam period and all the other exams. I don't know where that is in the chain of decision-making processes with the convener and the HOD. This has worked very well in the past with the relativistic quantum mechanics class that I've done. So in principle, there shouldn't be any issue. I imagine that when the booklet or the handbook comes out, then it will be whatever's in there is what will be official. I don't imagine the handbook is out yet.
Yes.
Okay.
They haven't released the project already. Quite funny. But
Okay, super. Then maybe I'll grab that from one of you to just sort of peruse. Okay, great. Super. Questions, comments, suggestions? I have sort of notes to myself to say that I'm very serious. I take this course very seriously. Spent a lot of time on this course, up till all hours working on the lectures, even though I've taught this before. And so there's a similar expectation on you, that I expect you to take the course seriously and for you to work hard. The bargain is that it should be rewarding and valuable for you, that it shouldn't be busy work that you're doing. But at the same time, I also want this to be a space where we all feel very comfortable. I want you to feel like you can ask questions at any time. I feel like this should be a respectful environment where any questions asked in respect will be treated respectfully. That's my, again, commitment to you. I feel like that's the best way to learn. And then there's just the honest fact that I'm getting old and I've been doing this for 25 years. And so it's hard for me, just honestly, to put myself in the mindset of somebody who's seeing this for the first time. Further, there's this standard cliche, which is nevertheless true, that if you have a question, it's very likely that everybody else in the class has a question, has that same question. So please don't feel bashful, and also this is a very good place for you to practice asking questions. So if you view yourself as going to become a working scientist, you're going to be going to conferences, an important part of that process is to ask questions of speakers. It's also going to be true if you go into the business world, people are going to make presentations. You need to become comfortable with engaging with speakers. As a concrete example, I had a student who asked a question in a conference, and after the talk, she was offered a postdoc. Yeah, it's very serious and it's very valuable. So view this as an opportunity, a safe space to engage with that action. I could turn my video on, perhaps. You can see me if you want. Super. Questions there? All right, great. So let's talk about the goals for the course. So in some sense, you are here because you have to be here, but I want you to be here because you want to be here. And thank you for those who are actually not in physics for joining. That's very, very rewarding for me, deeply meaningful. So thank you. So what I want you to do is I want you to leave the course with a solid foundation in the fundamentals of quantum mechanics. That's the goal. So as something of an outline, we will discuss the postulates of quantum mechanics. And in particular, spend a lot of time talking about abstract vector spaces. And then also the Hamiltonian formalism of classical mechanics. Just a quick sense, I imagine all of you have seen the Lagrangian and seen the Euler-Lagrange equations. Has everybody seen the Hamiltonian and Hamilton's equations of motion? Okay. Anybody online who has not seen the Hamiltonian form of the equations of motion in classical mechanics? Okay, great. Wow, and this will be very easy. And sorry, and with okay, so you've seen Hamilton's equations of motion. Have you seen the Poisson bracket in classical mechanics? Okay, good. Then there's something I can teach you. Very, very good. All right. So postulates of quantum mechanics, operators in various bases. So, for example, hopefully you will come to see that the Fourier transform is just a different way of seeing the same vector, abstract vector, which is the function in a different basis, position versus momentum basis. Along the same lines, we'll talk about the Schrödinger and the Heisenberg picture. These are analogous to the active and passive versions of transformations in classical mechanics. We want to solve the simple harmonic oscillator via algebraic methods. Sidney Coleman famously said that a physicist is somebody who, over the years, treats the simple harmonic oscillator with greater and greater levels of abstraction. So we're going to prepare you for quantum field theory with an abstract method of solving the simple harmonic oscillator. All right. Then entanglement and Bell's inequality. Basically, the experimental evidence that the world is quantum and not classical. Time permitting, we will touch on quantum computing. And then similarly, time permitting, the path integral formalism of quantum mechanics. And from the path integral, it's very easy to see classical as the h bar goes to zero limit of quantum mechanics, at least in the free, unconstrained case. Okay, any questions on the outline, comments, suggestions? Is there some topic that you particularly want to be covered that I can consider for a moment and then not cover? Okay, or legitimately, I might manage it. No comments on that. Well, yeah. We'll get there. Great. Other questions, comments? Super. So everything hopefully will be self-contained. There's a list of useful books in the handbook. There's not really any one good book on quantum mechanics at this level. So in a positive way and dispositive way, positive and negative way, you're going to have the opportunity to engage with several textbooks. And that'll help you as you become more mature as thinkers to learn a new topic by engaging with several sources. Good. But having said that, hopefully, or the goal is that my lecture notes and then the homework will be self-contained. All right, very good. So let's go to the postulates of quantum mechanics. Let's get to the meat of the matter. So we're going to spend quite a bit of time on these postulates of quantum mechanics. I'm going to lay them out. Some of the words may or may not be familiar. The formula may or may not be familiar. The goal will be to step-by-step go through these postulates and understand the mathematics behind them, the words that I'm using in detail. All right, so number one, the state of a system is represented by some ket psi that may be a function of t, which is an element of a Hilbert space. Just as a comment for those online, I don't see if you have a hand raised, you're behind me. So please just unmute yourself and ask a question at any time. Okay, super. So state of the system. Number two, observables are represented by permission operators. The commutation relations between operators is given by the Dirac quantization condition, which is to say that if you have two operators in classical mechanics or two quantities in classical mechanics, A and B, that have a Poisson bracket, which you may not have seen, but we will cover, a Poisson bracket that gives you something else, C. Then this goes over into quantum mechanics as the commutator between the operator A, the operator B equals I, operator C. One comment is I'm working in H bar equals 1 units. When I was in a class like this in grad school, I insisted on keeping H bar not 1 until one homework set at about 2 in the morning after pages and pages and pages, and I just could not get the H bars to work out unless I just set them all to 1 and everything worked. And then I realized, oh yeah, if I just use natural units, life is infinitely better. You could just restore the units at the very end. Nevertheless, performing dimensional analysis is enormously helpful for catching mistakes. I strongly encourage you to consider the dimensions of the objects that you're working with at all times. All right, super. All right, if a system is in a state psi, say at time t, then a measurement of an observable represented by some operator O hat will be one of the eigen values of, say, eigenvalues omega of O hat. I think you all know what eigenvalues are, but just for completeness, so I have O hat on some vector gives me the number omega with probability, say, P of omega proportional to the inner product of omega with psi of t modulus squared. So this probability can depend on time, for example. The state of the system continuously change often called collapse from this psi of t to the omega that's measured. And then finally, time evolution is given by Schrödinger's equation. Is that I partial t het psi of t is the Hamiltonian operator ket psi of t. Yeah.
Omega operating on the state omega, is that meant to be on the state side? Because you mentioned that it's in the state side, or
So in
is omega side
here or here?
Well, I mean, the same, but the first one.
Yeah, so here I'm just defining what an I value is.
Sure.
So I have this operator. It's acting on some vector that lives in the Hilbert space. And this vector is very special because when the operator acts on this vector, I get the vector back with just some complex number, potentially complex number multiplying it.
You said state side.
Yeah.
Earlier, is the state omega different from the state side?
Could be.
Okay.
Yeah. Good. Any other questions? Welcome. All right, great. So you could ask where the postulates of quantum mechanics come from. And that's a very, very good question. That's not a question that we're going to explore. We're going to take these as axioms, like what is a vector space? There's some axioms. And if your set of quantities obey those axioms, then it's a vector space. Since we're doing quantum mechanics, these are the axioms that our physics are going to obey. We will try to potentially motivate them a little bit, but we're just going to take them as a given. All right, great. So what we need to do is we need to start understanding these various things, in particular, Hilbert space, vectors living in a Hilbert space, observables, which are rather operators, so operators acting on a vector space, the classical mechanics of the Hamiltonian formalism, and in particular Poisson brackets. And that'll occupy us for the next, certainly this lecture, and then next lecture, I would say at least. Okay. Super. All right. Good. So what's a vector space? So we have dealt with vector spaces. You have dealt with vector spaces quite a bit already in your life. You know, R3, for example, being a vector space, I hat, J hat, K hat. We would like to generalize those properties that I think you have a good, firm, intuitive grasp on to be more general, to allow just to abstract away, which will allow us then to understand all the systems we care about in quantum mechanics. All right, so this is going to be, and I apologize, pretty dry, but we'll try to make it a little bit more interesting at some points. And this is an opportunity, I guess, for the more theory-minded people to be excited to do hardcore math, and for the more experimentally minded people to engage possibly for the last time with some more rigorous mathematics, and then you can be done with it and turn screws and measure things and do something valuable for the world, unlike the theorists. All right, super. So for all vectors, say vi, vj, vk in our vector space, so we have associativity of vector addition. And maybe something that we, as we go through this, is in what ways are these various properties of abstract vector spaces properties that we would really want in our physics? So associativity of vector addition says that vi plus vj plus vk, where vj and vk are grouped, is equal to the grouping of the vi plus vj grouped plus vk. And I guess I should also add, I'll need some scalars. So in general, one can be even more general and talk about fields and define what a field is. I get lost in that, to be perfectly frank. We're just going to use complex numbers. Good. All right. Good. So associativity of vector addition, commutativity of vector addition. So v plus vj is equal to vj plus vi. There's an identity element. Of vector addition. So there exists a unique zero that lives in the vector space, such that any, say, vi plus 0 is just equal to vi. So there are additive inverses. So for all, say, vi in v, there exists some vi inverse, which is also unique, such that vi plus this vi inverse is equal to the 0 element. People can be a little sloppy. Sometimes they'll use number 0 to represent the 0 vector. That drives me a bit nuts and can be confusing. So we'll try to avoid that. Okay. So compatibility. Of scalar multiplication with field multiplication. So we would like to ensure that alpha beta on vi is equal to alpha beta acting on vi. So notice that there's really two different things going on here, right? So we have the scalar multiplication, where we have some complex number multiplying the vector. And then we have another complex number multiplying some different vector, which is given by that original vector beta vi. And then over here, we have multiplication within the complex numbers, alpha beta, giving us some third number, gamma. And then that is scalar multiplication within the vector space. So these are different operations. This is not commutivity. Okay, good. Identity element. Scalar multiplication. So there's a one that's in our field. There's a one in the complex numbers, and that one acts the same way, bless you, in the field as it does in the vector space. So one, that's supposed to be just the number one, which I'm doing a terrible job of writing. Vi is equal to Vi. This one is in the complex numbers. 1 times alpha is alpha. Distributivity of scalar multiplication with respect to vector addition. It gets long, I'm sorry. So we have that alpha Vi plus Vj is alpha Vi plus alpha Vj. And then distributivity of scalar multiplication with respect to field addition. So we have that alpha plus beta acting on Vi is equal to alpha Vi plus beta Vi. So this, we're a little cavalier with notation, right? That this plus is very different from this plus, right? That this plus is acting within the vector space, and this plus is acting within the field. The reason why we can get away with this sloppy notation is because we're assuming these distributivity laws. Okay, great. Awesome. We're done with vector spaces, with the definition of vector spaces, unless there are any questions. Amazing. Okay, so let's define an inner product. Things are starting to get interesting now. So an inner product which I'm going to write as something that eats two vectors and spits out a scalar. Such that we have that Vi is greater than or equal to 0. And the inner product of Vi with itself is equal to 0 if and only if this Vi is the 0 vector. So I'm being very tedious here in my notation, and that's purposeful. You've probably seen Dirac's, I'm sure you've seen Dirac notation. It's very handy. It's a nice shorthand. We will get to how that mapping makes sense as used through the inner product. But for now, we're going to be very pedantic in the way that this is written. Okay, super. 2. The inner product of Vi with Vj is equal to the complex conjugate of the inner product of Vj with Vi. And then there's a linearity. So the inner product of Vi with alpha Vj plus beta Vk is equal to alpha inner product Vi Vj plus beta inner product Vi with Vk. All right, super. This complex conjugate nature, where we have in the first argument, then tells us that we have linearity with complex conjugation in the first argument. So the mathematical term for this is that the inner product is sesquilinear. Kind of a fun word, and it's a technically true word, so it's useful. Okay, good. So let's define a Hilbert space. So a Hilbert space is a complete inner product space. So here, complete means that sequences of points, well, I guess sequences of vectors in the Hilbert space converge to a vector in the Hilbert space. I'm being a little bit less rigorous than a mathematician would be. I just want to give you the sense of what this is. So the way to think about this is that, i.e., there are no holes in the vector space. So why do we need to work in a complete inner product space? And the point is that we need an inner product to compute amplitudes. Right? We said in our postulates that the probability of observing some quantity is related to overlap, and this overlap is the inner product. A way to think about this is how much of this state psi lies along the direction of omega, the vector omega. Good. So the probability of observing the state omega at time t is proportional to this inner product of omega with the state psi t modulus squared. And we need completeness so that we may describe any physical setup. we don't want to find ourselves in some situation where there is some physically realizable experiment that could occur that our mathematics can't handle. Why don't I maybe pause here for just a moment if there are any questions?
Hi.
Yeah.
Would you mind scrolling slightly up just so I can see that last axiom of an inner product space? Ah, thank you.
Yeah, so it's linearity in the second argument.
And then is there any sort of anti-linearity in the first?
That'll be
I
your
guess
homework.
that might. Okay.
So an excellent question. Thank you. I will pay you later. That was a joke. Somebody laughed in here in the room, so thank you for the person.
Don't worry, I chuckled. My mic was off.
Thank you. All right, very good. Good. Any other questions? Great. Okay, so this has all been very abstract, and very abstract is all well and good, but it's kind of a pain. So what we'd like to do is start working in a basis. So let's define, so work in a basis and work with complex coefficients. Of the basis that form any particular vector. So it's important to recognize that a vector exists outside of the particular basis. So I could imagine in this room choosing an x, a y, and a z, and I have some vector, and I could talk about the components of the vector in the particular reference frame that I choose. And that's all well and good, but I could also say rotate that reference frame. The components would change, but the vector itself does not. You all seem very comfortable with that. At some point in my life, that was a really profound statement. Okay. So a complete orthonormal basis of a vector space V is a set of vectors say V sub E, for which now, because I believe all of you have had quantum mechanics before, you're going to be familiar with the idea that we can have finite dimensional vector spaces, like say if we have spin out, spin down, the two-dimensional vector space. You're familiar with countably infinite dimensional vector spaces. So where we have a particle in infinite square well, for example, and then you can also have uncountably infinite vector spaces or bases for a vector space. For example, if we are on the real number line and we want to use the momentum eigenstates as a vector space or as a basis, excuse me. So I'm going to sort of talk about a number of things where I'm going to write down how it looks in either a finite dimensional vector space or countably infinite dimensional vector space, or when I'm thinking about using an uncountably infinite number of basis vectors, or uncountably infinite dimensional vector space. And this is where the infinities that we're going to deal with are where subtleties really creep in. Where I will try my best to point out where some of these subtleties might be important or might crop up. In general, the details are not that important. Things will basically work. But what I'll do is I'll also provide resources for you that talk about this. All right, great. So we can have in a finite dimensional or countably infinite vector space, we have that this set VE is a bunch of vectors which I label with n that live in the vector space, such that for any vector that lives in the vector space, I can decompose that vector in terms of these basis elements. And there's orthonormality, which says that the inner product between, say, the En state and the Em state is a Kronecker delta. And then in an uncountably infinite dimensional basis, VE is again some set En element of V, but now we have that if we have some vector in our space, the decomposition is given by an integral. And the inner product of En with Em is given by the Dirac delta function or the Dirac delta distribution. Is everybody familiar with Dirac deltas? Good. Subspaces. This is a sort of a kind of a throwaway. It's in all the books, so I'm including it. So a set of vectors that are, say, Vs, that's some subset of V that forms a vector space is a subspace. So obvious examples are the zero vector and the entire vector space itself. Great. Okay. So I have here a subsection that I call mathy stuff. First point is recall the Gram-Schmidt orthonormalization procedure. So if you have some basis that's not necessarily orthonormal, the Gram-Schmidt orthonormalization procedure is an algorithm which will generate for you the orthonormal basis. Anybody unhappy with that? Great. Remember also the Schwartz inequality. So this says that the inner or the modulus of the inner product of Vi with Vj is less than or equal to the modulus of Vi multiplying the modulus of Vj, where this modulus of some vector V, this is defined as the inner product of V with itself, which is guaranteed to be a real number greater than or equal to 0 by the postulate of, or just the definition of an inner product, which we then take a square root of. So what is it saying? It says the overlap of two vectors must be less than or equal to the multiplication of the lengths of the two vectors. And remember that you get equality when the vectors lie along each other. Ooh, I need to charge. And I've got the triangle inequality. So this says that if I add two vectors and ask for the length of the sum of the two vectors, that's less than or equal to the length of the first vector plus the length of the second vector. Length, just going to quickly write this, of the sum of two vectors is less than or equal to the sum of the lengths of the two vectors. So this is sort of giving you an idea of directionality in your abstract vector space. So if your two vectors are in the same direction and you add them, then the length of the sum of the vectors is equal to the sum of the lengths of the vectors. Otherwise, the two vectors are pointing in different directions. So their sum has got some components in one direction, some components in the other direction. All right, great. Good. So now let's get to some fun things. Unless there are any questions, which I don't think so. Okay, great. Dual space. So this is going to get a little bit mathy, but you are familiar with it. So the dual space, you've dealt with this quite a bit already in your life. We'll denote it with the V star of a vector space V. Is a set of all linear maps phi that eat a vector and spit out a scalar. And technically, this C should be a field, but we're always just going to be working with complex numbers in this class. And we'll suggestively write that for our phi in our dual vector space, we have what looks like a bra with phi, and then it's going to eat some vector v and spit out a complex number. That's what a linear functional does, or a linear map does. And this complex number will be phi v, bra phi ket v. All right, equipped with addition and scalar multiplication, where we talk about say phi plus psi as a linear map, which is phi plus psi, and alpha phi, which is the complex conjugate of alpha multiplying phi. The dual space itself becomes a vector space. And then the key point that, again, you've at least implicitly done from years now in your life, any sesquilinear form induces a mapping between a vector space V and the dual space V star. So we have that for all vectors V in our vector space, then if we stick that V vector in the first slot of our inner product or our sesquilinear form, but we're really thinking inner product, this is going to be an element of our dual space. So in particular, any product produces such a map. And what we'll do is utilize bracket notation. So we'll write all elements of V star as some bra, say VI in this V star, whose action on a vector V, say Vj, of our vector space V, is given by, say, our usual bracket notation Vi Vj. This is the inner product of the Vi with the Vj. So hopefully this provides a clear set of definitions for the objects that we're working in the vector space. Good. We've been very agnostic about the types of things that can live in a vector space and the type of operations that can be the pluses and multiplications. We're going to stick with the usual vector spaces that we use in quantum mechanics you've known and loved so far. But one could push it even further to be even more abstract if you want. Okay, so that's vectors, inner products, dual vectors. Next step is operators, unless there are any questions. Awesome. Okay. So we've gotten through postulate 1, now into postulate 2. All right. So an operator, call it O hat, acting on a vector space. Say V is a map that takes one vector, call it V ket in V, into another vector, say V prime, which is also an element of the vector space. So what we say is this operator acting on vector V, this is some other vector V prime. And it's often common to denote this V prime by bringing the operator inside of the ket. So just notation. Operators can act on dual vectors. So we can have some bra V operator O, which is equal to some bra V double prime, where in general, we don't have that the vector V double prime is equal to the vector V prime. It's only very special operators which have this property. So we define the Hermitian conjugate of an operator O hat as, so we start with bra V, operator O hat dagger. We define this as our inner product of the OV vector living in the dual space. And now this is the dual vector to V prime. Now, if the vector V double prime is equal to the vector V prime, then we say that the operator O is Hermitian. I have to say, this always trips me up. So you could ask a question, I could try to answer it, but I've got a specific problem in the homework where hopefully it'll give you a little bit of a feel for working with these types of objects. There's this difference between the operator being a map that maps vectors to vectors, which also maps dual vectors to dual vectors, but the dual vector of one vector, sorry, the dual vector that a dual vector V is mapped into is not necessarily the same as the vector that that same vector is mapped into. That, for me, at least, is tricky. So again, I think just working an example will be helpful there. Yes.
You're right. Ket V greater inside.
If I heard you correctly, the question was, can I look at the, maybe call this VI operator VJ, something like that?
So the prime operator inside.
Yeah.
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 Same thing.
Yes, but it gets tricky, right? So I could write, so we wrote operator O acting on V. This is V prime, which is O V like so. We could also write VO is equal to V double prime is equal to, I would guess I would write this as something like this, because I want to distinguish that. So if O is Hermitian, then this is equal to this. So just want to be a little careful there. Good, thank you. Other questions? Okay. Super. Let's come over here. Great. We'll be working with linear operators quite a bit. So a linear operator is such that for all vi and j in our vector space and all alpha and beta in our complex numbers, then our operator acting on alpha vi plus beta vj is equal to alpha operator on vi plus beta operator on vj. So addition of operators is associative and commutative. Okay. So the simplest example of an operator is the null operator. So we can consider the zero operator acting on some vector is equal to the zero vector. Sometimes it's nice just to like do the simplest thing and then you feel a little good about yourself. Ah, I've understood something. All right. So the second simplest operator is the identity operator. So the identity operator, which we'll write in this way. So for all vectors in our vector space, the one operator acting on the vector gives us the vector back. And the one operator acting on the dual vector gives us the same dual vector back. So is the identity operator Hermitian? Yes, very good. I want to say important subtlety when it comes to infinite dimensional vector spaces is the difference between Hermitian and self-adjoint. I hesitate to say important because it's important in the sense that it leads to some potentially, bless you, interesting mathematical complications, but doesn't really lead to particularly interesting physical complications. But I will provide you with a link to a document that goes into the details between the difference between Hermitian and self-adjoint. It boils down to the subtlety of whenever you have an operator, rigorously you need to define what's known as the domain of def operator. What vectors does that operator actually work on? And you can have operators that are Hermitian, but whose domain of definition, their Hermitian conjugate is in fact larger than the original domain of definition of the operator itself. This, the sort of example for this is the momentum operator when you're working on the real numbers. That the P dagger is in fact domain of definition is larger because of an integration by parts. And the consequence for this is that the basis vectors for the momentum operator on the real number line don't live in the vector space itself, right? They're the EVIKX's, and those are not normalizable. So it's a subtlety, but it's not really that important of a deal practically. We just work with the EVIKX's and go on our merry way. All right, super. Note that once the action of an operator on the basis vectors is known, then the action of the operator on any vector is known. This is a consequence of our linearity of operators. So it's then useful to define the projection operator. We'll call it a p hat I for a basis vector, say E sub I. So we'll define this as what we'll call the outer product. I want to call these not I's, but N's for consistency with before. I'm sorry. Okay. And notice that we can decompose the identity operator. We have a decomposition of, which is the sum over n of the PNs, which is a sum over n of these outer products, or is an integral over n for PNs, which is an integral over n of the outer product of the ENs, depending on whether we are in the finite dimensional vector space or if we're using a countably infinite dimensional set of basis vectors, or if we're using the uncountably infinite number of basis states. So this decomposition of unity represents the completeness of the complete orthonormal basis set. What one finds in, for example, quantum field theory is that one of the very few things you can do is assume that there is a decomposition of unity. There's not a lot of things we can do in physics or math, but multiplying by one is one of the few things we can do. And it's actually exceedingly helpful. It's all about choosing a very clever one. Okay, so you can find a representation of any vector using your basis. So for example, we could have a vector v. We can multiply by one of the very few things we can do. We write that one as our decomposition of unity in terms of projection operators. So this becomes a sum of this outer product acting on the vector v. And if we call this inner product of the En with the V, this is our An. We have explicitly constructed the coefficients in our basis. And we do the same procedure if we have an uncountably infinite number of basis vectors. And now instead of counting our ANs, our A's will be a function of N. Yeah, just thinking, what's the right logical order? Yeah, I think if we assume that the basis, well, the fact that it is a basis tells us that we can decompose any vector in the way that I've shown, then I can see that that shows that the identity can be written as a sum of the projection operators. I think I've taken here a different slant, which is to say, let's assume, perhaps I could say, let's assume I have a subset of vectors such that the sum of the outer products of those vectors gives me the identity. Then I have the property that that set of vectors is a basis. Yeah. Good. All right. Now, it's often the case that you would like to switch between different bases. So you might want to think about measuring the spin of some object along the z direction, or you might want to measure the spin along the x direction. Those are two different bases spanning the same vector space. And in a similar way, you could think about asking, what does a function look like in the position basis? What does a function look like in frequency space? Same function, same vector, different bases. How do you transform between those bases? Okay, so suppose one has another complete orthonormal basis. Let's call it some VE twiddle. Then our vector V is 1 times V, because we can only multiply by 1. Very little we know how to do. En on V, sum of the outer product, En, V, although these are not all the twiddles. And so this is equal to An twiddle, En twiddle. Or similarly, it's the integral dn of a twiddle of n, En twiddle. So one has that this An twiddle, this is our inner product of en twiddle with our vector v. And we can again shovel in our identity operator. So what we have here is we've got the sum over the ANs and then the inner product between the bases. So the above changing basis naturally gives, for example, the Fourier transform. It's just one of infinitely many different ways that you can choose bases for a function space. Okay, good. So we talked about how it's nice to work with the components of a vector. Nice to think about abstract vector spaces, but it's nice to work with something concrete. It's also nice to work with the matrix element of operators. So this is the way of representing the operator in a particular basis. So, everything okay?
What will follow the basis and proceed Hibbs?
Naturally.
Thank you.
Yeah, otherwise known as chicken scratch. All right, I'll try to be a little less, yeah. All right. I will slide in and out of chicken scratch. So you sort of keep nudging me. All right, cool. So general operator is represented by its matrix element on a particular basis. So we have our operator O. What can we do? The only thing we can do generally, which is multiply by a 1. And so if we are in some finite number of basis vectors land, then we have a sum over, say, n and m of our projection operator n, our operator O, our projection m, sum over n and m. So this is our en operator, em outer product em. So let's call this thing in here the matrix element. We'll call it ONM. So it has 2 indices like a matrix. And we can use our usual Einstein summation convention and usual matrix multiplication when we work with these objects. And so this is equal to the sum over n and m of O and m, and then the outer product en, em. So you can see why working in a basis for which your operator is diagonal is nice, because then you only have a single sum, not 2 sums. Or if you have the situation where you have an uncountably infinite number of basis vectors with dn, dm, pn, o, em, integral dn, dm, blah, blah, blah. So this will be integral dn, dm of operator O, which is a function of n and m, en, em. So, So in a basis for which the operator is diagonal, then En operator Em is proportional to a delta Nm or a Dirac delta Nm. And so then we have that our operator O is equal to a sum only over n of, say, ONN En, or maybe we should call it On, or an integral dn of our operator. Is it just a function of n? So a far simpler representation. So we would like to seek out bases for which the operators we're interested in are diagonal. Okay. So we may work out the matrix elements of the Hermitian conjugate of our operator in terms of the matrix elements of the operator O. So we would like to know what is EIO hat EJ. Sorry, this is the O hat EI, because we're working with the Hermitian conjugate. So this is our EIO dagger EJ. And this is going to be our O dagger matrix element IJ. But we know that specifically this inner product, by the definition of inner products, is equal to this inner product complex conjugated. Right? If I swap the order of the inner products, I just get a complex conjugate. We can expand what we have inside of here, inside of these parentheses. This is EJ O EI, sorry. And then complex conjugated. And this is nothing but matrix element operator O with now J and I swapped, and this thing complex conjugated. So therefore, the matrix element of the Hermitian conjugated operator, the ijth component, is the jth component of the matrix element for the operator complex conjugated. So the famous complex conjugate transpose for Hermitian conjugation. Okay. So hopefully this is sort of like, this is where these things are coming. Good. So consider the motivation of operators in a particular basis. So we could consider an operator O1 multiplying some operator O2. And we can consider the matrix element of this. So we multiply by a bunch of different ones. So this is 1, operator 1, 1, operator 2, 1. And so then we've got a sum over I, J, and K. Outer product EI, outer product EI, O1, EJ, EJ outer product operator O2, EK, EK. This is sum over I, J, and K of the matrix element O1, I, J, matrix element O2, J, K, and then the outer product EI with EK. So this is our usual matrix multiplication. Hence why we call these objects matrix elements. So for uncountably infinite dimensional basis, then we'll have a similar situation. It's be an integral over dn1, dn2, dn3 operator that's a function of n1 and n2, operator as a function of n2 and n3, and then the outer product of n1 with n3. Great. Now, remember that in our postulates of the quantum mechanics, we said that observables are represented by Hermitian operators. Sorry, are you okay? Okay, cool. It's okay if you're not. All right. So we talked about how we have Hermitian operators. Why did we specify Hermitian operators? Any idea why we require Hermitian operators?
Would it be because they have real eigenvalues?
Awesome. So thank you very much, online and in person. Exactly. So we know that we never measure any imaginary numbers or any imaginary component of complex number. Everything we measure in real life is real. So it better be that any observable, we're guaranteed that the quantity that we measure is real. And we said that our postulate of quantum mechanics is that the possible values that can be measured are the eigenvalues of the operator that represents the observable. And so it better be such that that operator gives us real eigenvalues. And what guarantees us an operator that gives us real eigenvalues? Those are Hermitian operators. Good. There's been recent work where people have thought about relaxing that restriction to slightly more general operators, but we're going to stick with Hermitian operators. Good. So why do we require that observables are represented by Hermitian operators? Because Hermitian operators have real eigenvalues. Remember that we only ever measure real quantities, and that we can only ever measure the eigenvalue of an operator that represents an observable. Okay. Good. What's another nice property of Hermitian operators that you may remember. Yeah.
It's its own complex conjugate transpose or something.
Yeah, I mean, we just showed that, and that's useful, and that's related to why the eigenvalues are real. So that is very important. But when would we like to make sure that the math that we use to describe physics allows us to capture any possible measured state? Right. So at this point, what we've done is we've said that the eigenvalues of our Hermitian operator are real. So that means it's a nice candidate to represent observables. But we also want to make sure that any possible measurement can be captured by an operator that represents a measurement. And we said that when we make a measurement, the possible values of the measurement are the eigenvalues, but that the state that the system turns into is an eigenket. So we need to ensure that whatever we use to represent observables, its eigenkets form a basis for the vector space. We need to be able to take any potential setup of a physical system and decompose it into the basis states of the operator that represents the observer. And we're guaranteed by spectral decomposition theorem, we're not going to go into in detail, that a Hermitian operator has that decomposition. And we can always measure the physical state of a system and assign definite probabilities for any particular measurement. Okay. Super. I don't really want to go into, well, I guess further. And then 3. Eigenkets associated with different eigenvalues are orthogonal. Right. You can't you don't have any ambiguity in terms of probabilities of particular measurements. Good. Okay. Okay, we've got a few more minutes. Power through to the end. All right. We say that 2 observables are compatible if their commutator is 0. So two observables A hat and B hat are compatible. The commutator with A and B is equal to 0. And incompatible. The commutator of A and B is not equal to 0. And the point of defining the compatibility and incompatibility is that suppose that the commutator of A and B is 0, and the eigenvalues of A are non-degenerate. Which is to say none of them repeat. Then B is diagonal. In the basis of the eigenkets of A. So we can write B as some sum over coefficients Bn of the outer product of the eigenkets of A, which we call An. So the canonical example would be, for example, spin in one particular direction and then the spin operator squared. Those two operators commute, so they're simultaneously diagonalizable. And so we can then label our states with the A and B eigenvalues. Right, so we label a particular spin state by the S squared and the SC. Okay, I feel good about where we've gotten to. Clock on the wall is not right. We're at 9:44. How do we feel? Well, actually, let me ask if there are any questions. All right, then if there aren't, what I'll do is I will stop the recording. I see there's a comment in the chat. I apologize that I missed it. Here we go. I haven't. Okay, 8:13 a.m. Thank you, Mohammed. Good. All right, let me stop recording.